Okay. All right. All right. How's everyone doing?
Pretty good.
Not good, huh?
I think we're
Relax, everyone. Is your money? Oh, I forgot to make more money. Where's your Trinity?
good. About where it's at.
I didn't eat the money now.
Oh, I think. Oh,
You tell me how much you had, I can.
yeah.
It's go into Canvas. I think it's something like 120 something.
I wanna say it's like 125, that might be a little high. Go into Canvas.
So you start counting 120.
Go into Canvas and look, there's a better sheet that has everyone's current totals, and then I made a line graph. Some of the faculty wanna make a side
I
bit
saw that.
Yeah.
on
Sarah's at 120.
Exactly.
look at my good memory.
Thanks, Trinity.
Thank you.
So that is 50, I believe that's 120, but put your name on the thing, please.
Thank you.
Okay, so homework is due on Friday. Hopefully everyone saw that.
Yeah.
Did I change the date?
We don't have class on
How
Friday.
do we turn it in?
You can just put in the mailbox.
Okay.
Okay, good. Some folks, if you already understood the Monty Hall problem and you thought, wow, that's way too easy and boring, I've pitched another problem about red or green balls. Remember that one?
Yeah.
Does that one make sense?
Yeah. I think so.
Makes perfect sense,
At first, I
even
didn't,
though everyone got it wrong.
at first, I didn't know whether or not the number of balls would go down.
The ball does go down, right? But does that matter?
No.
Why?
Because you said it was something else.
Because if you watch it back, you can figure it out, right? But why is it the case that when I pull a red ball, that changes what we should think about the next red ball that we pull? You know, our instincts tell us that we have one less red ball, so therefore the probability, the choices goes down. Right? But there are some conditional probabilities there that we're not taking into account. Right? So what does getting a red ball on the first try tell you about the distribution of red balls?
The red balls, there's probably more red balls than green balls.
There's probably more red balls than green balls. Because if it were not the case, let's say there were very few red balls, what would you be likely to draw on your first draw?
Green.
Green. Right? That makes sense?
It does, but I think it just annoys me because it ignores the fact that like.
Yeah, doesn't feel good. But think about it this way, right? So let's imagine it's 50-50. You're right. So if it's 50-50 and you draw the red ball, then there's 49 out of 99. That's still pretty close to 50-50, right? But if you drew, right, from a distribution which is mostly red balls, so your chance of grabbing a red ball is high, right? Then you're very likely to grab a red. Whereas if you grabbed a ball from a distribution that is mostly green, then it's very rare that you would grab a red ball. Like, let's say there's only one red ball in that entire base or whatever, right? That's an exception to the rule, right? But the idea of likelihood makes us walk away from these chance encounters, right? We don't want to think about, well, I can think of one specific example in which you're wrong. We want to think about what is the most likely thing that's going to happen, right? Okay. So we talked about probability, and we're gonna have to rewire our brains in this discussion, how we think about probability, right? And in particular, we are thinking about the terms or and. So let's go back to the drawing board and just refresh our brains. Okay, the probability of two things happening, one or the other, how do I write that? A and B. A union B, is that right? this. And how would that be written?
Probability A plus,
Oops. Good,
the probability B minus their intersection.
very good. Oops. And how do I write the intersection again? I'm good at it, this.
A and B.
A,
Up and down, you.
B, good, perfect. Okay, and now let's say I want both of them to happen. A and B.
And just remove the intersections.
Just remove the intersection, what do you mean by that?
Or just like, not remove it, but just like. Only factor in like probability of A and probability of B.
So this means or when we think about probabilities,
Yeah.
and I'm asking a separate question.
Okay.
A and B is represented by what?
Oh, okay, so that's kind of given.
Ah, very good, it's already on you. So this is A and B. The intersection is and, right? And now we have to be a little careful. Right? Because the intersection of A and B, the chance of you drawing an ace and a spade, right? Is different than ace or a spade. So here we were subtracting off the chance that it was both of them, right? Okay. But now we have to ask a question about this type of and. Because we can have probabilities that are independent. So if, for example, I pull out my handy dandy die, which everyone's been using in their free time to, right? Okay. So let's grab some 2 die. I roll 1, right? The probability of rolling a 6. Oh, wow, that was really cool. I did it. And is the probability of rolling a 6 here conditional on that one?
No.
No. So if they are what we call mutually exclusive events, how would I draw the probability? Or how would I write the probability here?
Multiply.
Exactly right. So I'm gonna write something like the probability of A times the probability of B. Okay. And how is that modified? So let's say this is the mutually exclusive event, ME. How do I write this where one is conditional on the other?
Right here.
Yeah. So this was an example where rolling 1 was not dependent on the next. But let's say it's a different type of event. Let's say I'm a delivery driver and I'm going from Amazon warehouse to your home. But I'm only allowed to make right turns, right? Because that's, well, you don't know about this, right? You know that delivery drivers try to optimize their route so they never take a left turn? Because waiting at a left costs more time. Whereas turning right, you can turn right on red in most places. So you can think about a delivery route, right? And we're gonna do an example of a very stupid version of this, where you have to make choices at every location, okay? And they can be conditional choices. So maybe if I took a left recently, I'm prohibited from taking a left, right? Maybe I only get 1 left per 15 minutes, okay? So that would be a conditional probability. So now how do I write this probability?
Oh, A vertical slash B.
Okay, good. So now we have our new one, which is the probability of
B given A.
B given A. And that's what this one is here, given. Okay. Okay. So let us try something. Yeah, let's do an example of this. Someone have their die?
Yeah.
Okay. You have your die?
Yeah.
Yeah, everyone in the room. All right. So you should take 2 die. Just select 2. And now roll them. Okay, and what I want you to do is I want you to write down the results of your 2 die. Tell me what they are. Rolando?
5 and 3.
Isabel? 4 and 2? You assume that my eyes work. Okay, 2 and 1?
3 and 4.
Those will be important for this game. In a way that won't make any sense until we do it. Quickly, take die. Spin die. Roll 2 die and tell me what you have. I know, this doesn't look like math, right? But I promise it's still mathematical.
That's amazing. You accidentally got the kids to the dice game.
Okay. So this is a very fun game. Okay. So this is node A1. This is node A2. This is node A3. And this is node A4. Okay? All right. What was your dice roll on?
4 and 6.
What we're gonna do here is we're gonna start at the origin at O. And we are going to randomly go off in one of the directions that is connected to O. Okay? And at every junction that's marked by a dot, we will make a random selection of the available choices. Now you can't go backwards, right, along this track. You can only move in the direction of the arrows. What's the probability that if I start at O, I get to B? And how much money do you want to put on it based on the roll that you just got? What? Okay, let's say that again. Okay. I start at O. I will be randomly selecting, and we're going to use an even distribution. So I'll, if there's 4 choices, it's 1 out of 4. If there's 3 choices, it's 1 out of 3. Okay. Now, at every junction, I'll have to make that choice. Okay. So I want to know what the likelihood is that I go from O to B.
Assume this, but between B and O, it goes up, right?
Oh, sorry. Yeah, let me do no, so this goes down like this, and then this one goes down like that. Very good. Good eye. Okay. So there are several paths, and before you start writing them all down, okay, do you understand the premise of the game?
How is like the direction determined? I know it's like random, but like.
So here it'd be any of the 4 junctions. So we'll do it one example, and then I'll talk about the mathematics we'll use this, and then we'll make the bet, and then we'll find out what the probability is. Okay? All right. So first here, let's start here randomly.
Yeah.
Number 1 through 4. 3. Okay. 1, 2, 3. I head to here. Now I have 3 choices. I can't go back this way. I can go one of these 3. Number 1 through 3. 2. 1, 2, I get it. You see? Okay.
But are you gonna decide which one starts with one every one?
No, we have a calculated probability. The bet will be, you roll the numbers. Those numbers will tell me whether or not you're inside or outside of the probability.
Okay.
I know what the probability is because it's written. Okay, so I selected numbers within some range, but you don't know what the range is yet. And if your numbers are those numbers, we're good. Does that make sense?
Yeah.
Fun, right? Okay, so let's discuss the math really quickly. Okay. We saw that for a single conditional, right? This would be an example of a conditional probability, right? Because you start off by making some selection in the direction away from O. Now you're gonna have to do the step away from O, no matter what. So that one, fine. But then you have to think about the conditional probability of the rest of them, right? So how do I do multiple steps? Okay, that's your first question. So in fact, I can write, generally speaking, that the probability of A union B is the sum of the probabilities. Oh, fuck. Oh, that one. Yeah. Sum of the probabilities of AI union, oops. Okay. You could also say something along the lines of, if you divide both sides by the probability of B occurring, right? With this equation here, you could write that the probability of A given B is going to be the sum of the probabilities of A I. Okay. So this is what we call the addition law for conditional probabilities. Okay. The final one, so this would be, maybe I'll just say that here. And so we see how that happened. Okay, you divide by that to get to here. And the one that we really give a shit about is, did we get to B? Right? So how do we do that? Well, the probability of B is equal to the sum I of the probability of AI times the probability of B given the I. So that is gonna look really murky and it's not gonna feel very good until we use it. Because it's done, right? You're like, oh, that doesn't mean anything to me, good luck. Right? Okay. So this is what we will use to solve that for sure. But now we want to tap into those intuition fields. So what do we think? How much money do we want to put here? What? $1? You don't have to bet, but if you bet, it has to be $1.
Let's do it all. One more.
One more.
I want to bet 40.
You want to bet 5?
I don't know why. Let me know what's happening.
How much you betting on that?
I'll bet 20.
I feel $1.
You're just still going $1? $10. Oh, look at the distribution of numbers we have.
So you,
Oh, big spender. What's that?
20.
20.
Oh wait, we have to have good numbers, right?
Yeah, you have to have rolled the number that I think is correct.
Oh wait,
That I think
can I
is.
switch my bet to $1?
You can choose for $1. So what do we think the probability is? Better than 50-50? No, you don't think it's better than 50. Raise your hand if you think it's better than 50-50. So why are any of you betting?
I feel like.
Because it's fun, okay, as long as it's fun, okay. So we don't think that the probability is better than 50-50. How bad is it? You know, if I put a gun to your head, are you gonna think it's better?
No.
Okay, so those are the extremes, right? Money and your life, right? When we're thinking about, right, there's a game called Russian roulette. You heard about this?
Yeah.
You can't say you love this game. No one loves this game.
It's like, okay, they with like chocolates and like stuff
Play with
and
the
like
dark
hot sauce.
Okay, all right, much lower stakes, much more easy to love. So in this game, what are your odds?
1 out of 6.
36. What kind of gun are you?
Does order matter?
Yeah.
Likes you guys.
What do you mean? So you have,
So you're saying that you.
How-
one of
sorry,
our-
not this game, in Russian roulette.
Oh.
Gun do you use?
We always use a revolver, right? 'Cause the game with the gun, you open the cartridge, you put the bullet, and then you spin it, and then you close it. So maybe you get lucky and someone's got like an 8 shooter, but usually you have a 5 or a 6 shooter. Those are not good odds for your life,
Yeah.
right? And they go down every time someone survives. They go down dramatically. Okay, so usually we think about these terms, right? Cash and money. And the probability, the way that we interpret probability can sometimes be as drastic as that second. Because something with a very low probability, but a very high cost if it happens, is something we have to analyze when we think about spacecraft design, when we think about climate change predictions, right? Okay, low probability of it happening, but if it kills millions of people, you still want to prevent it, right? Okay. So here, cost is not very high, so you bet. What do we think the probability is? Low, like 10%, low, like 5%? How are we gauging that feeling?
I'm thinking 40%.
Each
No.
junction's like 30%.
Okay,
Well, the first junction is like 25%.
No,
Oh,
there's 2 chances.
There's
Flip
2
that
chances,
one's
so it's
50%.
50%. And then if you go to the left one, you have a 1 in 3 chance.
I think it starts off at 50, and then every time you hit one that doesn't directly bring you to B, it drops you down a lower percentage.
I think because it's conditional, yeah.
Cause it's conditional.
it's conditional, yeah.
Yeah,
Okay.
it's the, if given, A given B.
Okay, so I've given you a thing. So, do you feel like you can use this? Do you feel like you understand what it says?
Yeah.
Wait, can I ask again what A and B are? Like, what do you define A and B as?
So B is the probability of the event B happening,
Yeah,
okay? And that is equal to the sum of the probability of A happening times the probability of B given A.
right, what do we say the events are? Like this
So-
to B from A?
Yeah, so for example, the probability of getting to B, arriving at B, given the probability of making the right choice at A junction, right? The probability of B given that junction. You see?
Yeah,
Okay, and notice this is a sum.
yeah.
So even though this is the multiplication of 2 things which are a fraction, obviously less than 1, we're gonna add up here. So it's a competing balance, yeah.
You said the right choice, are we only adding up the probabilities of going the direction that would give you A? Or would you not include the wrong directions there?
Only the probabilities of the directions that give you B.
Yeah.
Right?
Because the other ones would multiply to be 0?
Exactly right. So we can just throw out anything that heads us not towards B, because the probability of B given A at those junctions, right? So let's say I had in this branch. A3 branch, right? Anything that I go in that direction is you're fucked, right? Okay.
Or A4.
Oh, what?
No, A4 has like 2 chances.
Yeah, A4, you know, surprisingly has 2 chances. And the more that you look at it, you're like, oh, okay, all right, talk yourself into it. So I'll give you 5 seconds to think about this problem, and then we'll do it on the board. Not 5 seconds, few minutes, okay?
We talked about it.
Yeah, you can talk about it if you like, compare up.
Someone talks to me.
Sarah,
And
we got, so start at 0. We have 2 chances of being correct.
if you get to A4, that's a 15%, and then from there, those are 100%, because those are the only directions you can go. But if you go to A1, then it's 1/3. Which is pretty good.
We're only building 2 die.
We're only running 2 dimes, what?
Yeah, so you go
Either
E4,
Either no.
yeah,
Hold on, the die don't have, is this your one?
oh, yes, sorry.
The die don't have anything to do with your selections here.
Then what do they mean?
They are numbers that will identify for me whether or not you happen to get the right path.
But how are they doing that if they're not telling you what path you're taking?
Is it like evens are right, or, and then.
Something similar to that. There is a range, so the probability, I know the number, right? It's a number greater than 0 and less than 1. And so your number is gonna fit into that probability range. In a way that I'll show you. It's a very dumb way, but I had to get you to bet on something, or to get the money flowing in the day.
Yeah.
A higher bet, they got free.
Really specific, really.
The answer is 42. Hitchhiker's Guide to the Galaxy. A must
yeah.
read.
Oh, yeah, that.
Okay, focus though.
So A, I think it's A1, that's the one. of the reasons.
Yeah, actually, I think something like that is the same for you.
Um,
Like, I think that- that was-
so B given A, so like, what's your chances of getting to B if you were to go to A4? Yes, I think so. Yeah, because there are 2.
It's big.
Okay, everyone take a different junction then. You can work together if you don't want to do all the math. Yeah, got it.
I mean, I did something. I got
I did something. That's my favorite version. Something occurred.
I think it's wrong.
Oh, I think I get it.
Ready? What are you doing? Yeah, we can talk about it. What are we doing? Is it cry? You don't have to cry.
I start off with every single one of the A1, A2, A3, A4 for that.
Okay, so let's start with the A1 junction. What do you get?
Like the probability of it to be 1/3.
Okay, so the probability of getting to B, given that I went through A1.
Oh, I got 112.
No, the probability just from A1,
Oh, 1/3.
1/3. Do you see?
Oh, from A1 itself, yeah.
Yeah, you're going 2 steps. That's totally okay, but just this step,
Okay.
we claim because there's 3 channels and only one of them brings you, but we still think about probabilities the right way. Okay, so 1/3. Oh, fuck. Next, A2. So the probability of B given E2 is,
Also,
all right? Good. All right, and then A3? Awesome, I love when the probability is 0, so then you don't have to calculate it. And the final one? 1/2, why? Right, so there's 2 out of 4. Okay, so the first junctions that are available, we'll notice that this junction here, did this matter? No, so just that, right? Why even draw this one? Because we'll draw the curved line.
I think it was 1/2 times 1, I was like, wait.
Yeah. Okay, so this says, once I've calculated the conditional probabilities, I simply have to multiply them by the probability that I get to any of those junctions in the first place. So let's take one step backwards. So what do I multiply these all by?
1/4.
Okay, so the probability, God, I'm really bad at this sometimes. The probability of AI is 1 out of 4. Okay. Good, 4 separate options. Okay, so what is the probability that I get to D?
20/96.
I don't get that.
We're not fortunate.
Wait, real quick, how is the probability of given 82, how is that 1/5?
That's a very.
Oh, 1/3.
Okay, so I have 1/4 multiplying all of these. And I
Okay,
have 1/3 plus 1/3 plus 0 plus 1/4. 1/2.
okay, I got 22%.
Okay. What number did you get? One over the other? I got 2/3.
I got 28/9, 14/48.
It might be similar. Do it one more time. 14/48. Is that 7/24?
14/48.
That's what I have. I have this number. And that you said was in decimal.
22%.
0, 1, 2, 2. Okay. Let's see who wins their money back.
Let's go.
Not Rolando,
29%.
because your number needed to be smaller than 22%. Does that make sense?
Sarah,
What do you mean your number need to be smaller than 22%?
Oh, like the actual digits themselves need to be less.
No, just this number. I only rolled 2 die to mess with you. So what I was looking for is if I'm generous and I say, well, 7 out of 24, that's not something that's represented on the die, but if I move that to an 8 out of 24, what is that? 8 out of 24, how does that reduce?
Oh, that's 1/3.
1/3. And there are 6 faces on the die. So the numbers 1 and 2 here are the ones that will win you money.
Damn.
so Sarah,
So Sarah wins $5. And everyone else has to pay me.
Look
Is
at
that-
me, I should have bet more.
maybe you put it at 0.
No, I don't go, no, they're fine.
Oh, you lose money. That's the part of the betting, right? Thank you very much. Okay, one good trick of the day. How does that feel? How does that process feel? We can do another one.
Stupid.
You say stupid? You can say stupid, that's perfectly fine. Stupid is a good answer. It takes a lot of getting used to. There's a dumber one that we'll do in a few seconds.
Okay.
It's okay? Okay. I was having a very funny conversation with one of my friends and his wife. They're both my friends, but I was mostly just talking to him. We were talking about probability, and I was like, I'm gonna teach them Bayes' theorem tomorrow. So we're gonna learn Bayes' theorem, which is spelled B-A-Y-E-S. And he's like, oh, you mean Bayes' theorem, B-A-E? You get it. You get it. It's Valentine's Day soon. You gotta have these bad statistical jokes ready, you know, for your partner or whoever. All right. So in fact, what you're gonna learn right now is the basis of what we call Bayesian statistics, Bayesian probability. It's all this dude Bayes. And there are some philosophical ramifications for what we're gonna describe. Now, you may have noticed, right, this has not really been physics C class. You know, there's no like first principles that we're like, oh, you know, there's an inertial law of force equals ma, right? There's nothing like that. It's like that number goes with this number. How? I don't know, it just does, right? So there's some like mathematical axioms that we build laws off of. But those can be argued. So far, we haven't argued about laws, right? We've just sort of accepted them. And I'm gonna present you with Bayes' theorem first. And then when we get into statistics themselves, you'll see why there are two interpretations to statistics. And these groups fight, not like with, what were the words? No, no, no. A frequentist would never play Russian roulette. Okay. And you'll see why that's a funny joke in like 6 weeks. Okay, so what is Bayes' theorem? We wrote there was an equivalence here that the probability of A times the probability of B given A. Remember what that's equal to? Probability of B times
A given B.
A given B. Okay. So let's do the dumbest thing possible. Okay. I'm gonna write this by itself. Let's just divide by B. Okay. So I'm gonna say the probability of A given B is equal to the probability of A divided by the probability of B multiplied by the probability of B given A. Okay, and this is basic. Okay, well, that's really not that bad, right? You're like, that doesn't seem like something to fight about, right? So let's define this in a different way. This shows pretty clearly, right? That the probability of A given B is not equal to the probability of B given A. Unless these are the same. Right? The only way, because otherwise one of them is bigger than the other. So they're not equal in any case. We could rewrite probability of B. How would I do that? In terms of like A's and some other letters that we've thought about recently.
So using Bayes' theorem, we can just divide it by probability of B given A.
Well, what I want to do here is I want to think about it's gonna be a little tricky to think about. So remember, we have some sample space. And we have the events A, B. And we want a conditional probability, but we now want to redefine B in terms of some other factors. In particular, I'll just write it out for you because I don't think this is maybe guessable like I thought it would be. We're gonna use the complement. So we haven't discussed that since last Wednesday, but we're gonna write that the probability of B is really the probability of A plus the probability of B given A plus the probability of not A. When I put that little thing on top, that's the complement. That is all of the probability space that doesn't include the A events. Does that make sense? Okay. Times the probability of B given not A. Do we see why that is? Okay, so let's break this down. A conditional probability, let's think about it in terms of getting, how do I always erase stuff that I want to use 2 seconds later? So we wanted to go from the origin down to the B locations. The probability of getting to B, oh, I don't know why I did this. This is my bad. This is multiplied. This is probability of A multiplied by the probability of B given A. Okay, so let's think about it in 2 different ways. This is the probability of going through the junctions that get us to B. Probability of A, 1/4, times the probability of going through the junctions that get us to A. Okay? Plus the probability of not getting to those junctions. 0. Times the complement. So that's kind of a dumb example, but this is how we think about the sample space as a whole. Because this is the probability of the choices we want. And this is the probability of the choices we don't want. And that together is the probability of all of the choices, right? And then the only thing is here is how does B interact with those different choices? So what's the probability of getting to B given all the choices we don't want? And the probability of getting to B given all the choices we do want? Well, that would just be by definition B. That is the definition of the probability.
The stuff we do want, is that always gonna be less than that, or no?
What's that now?
Like for stuff we do want for probability of B, is the right side gonna be less than the left side?
Very interesting. Very interesting question. And we're gonna get to this when we think about why you shouldn't go to the doctor's office too much. What? Krismani? Don't be healthy? Okay, we're gonna think about this in the context of what does it mean to get a positive diagnosis? Okay? Because there's things we have to take into account. And we can think of this in the context of an example that we're about to do, which is, let's say, I'll just pose it right now and then I'll rewrite Bayes' theorem. You go to the health center. They say you're positive. Right? I was so careful. So what's the probability that you actually have whatever it is they diagnosed you? Did you know that it's not 100%?
The test.
Yeah, so what are the things that could go wrong? So let's, there's false positives. There's the opposite of false positive, which are false negatives. There is the distribution of the people who are healthy and the distribution of the people who are unhealthy, right? So all of these are populations. And when we think about utilizing Bayes' theorem, we have to calculate what the likelihood is that with a with a positive test, what is the likelihood that you have the result? You see? Because sometimes you you do the COVID test, a little faint line,
Yeah.
right? I don't know, is that real? Or is that just like mascara, like, I don't know. Blush that came off, right? Something pink that makes the line. Right? That makes sense? Okay. So let me rewrite Bayes' theorem using this new idea. Okay, this is the form of Bayes' theorem that you'll see most common, and it's the one that you'll probably end up using the most. So we're gonna rewrite this, we're gonna add this piece into here and move this into the top. So what is the probability of A given B? Well, that's not too bad. On the numerator, wait, which one's numerator is top? The probability of A multiplied by the probability of B given B. Cool. And that's going to be divided by the probability of A times the probability of B given A plus the probability of A complement to everything that's not A times the probability of B given A complement. Okay, is that reasonable? So this is the Bayes' theorem that you want. We do another dice roll. Want to see if you have COVID? Okay, so let's do you want to do 2 dice or, yeah, let's do 2 dice. We know what you got.
I got 6 and 4.
6 and 1. 6 and 1.
I know, I just have to remember how to spell everyone's names. I'm really bad at spelling, like really bad. You want me to?
Start with an I.
There you go.
9 and 3. Spell it wrong.
Right.
Oh, yeah. There you go, read. That's pretty good. The A. You ever do that? 5 and 1? Wait, so you said 5 and 1 or 6 and 2?
I got, 1 and 3. My name's already spelled wrong.
Do I spell it wrong every
I
time?
know, it's spelled wrong with I.
TRIN.
ITI. It birth certificate already wrong. It's okay.
What is it supposed to be?
Trinity spelled with a Y.
Oh,
I
you're
know,
going
I-
I at the end.
Like a noun.
Like
Oh
that?
my god.
He's gonna forget the
He
numbers.
doesn't,
every time.
yeah, and I didn't mess it up, yeah.
Yeah, I had no idea what your numbers were. 1 and 3?
Yeah.
Okay. All right, so let's do some numbers. You go into the health center. You're taking a blood test. It's a PCR test. Here's the thing. We have to talk about positive test rates and negative test rates. So for people not, sorry. For people who are infected with the disease, the positive rate is 99%. Okay. Of people infected. Sorry, for people not infected, a false positive rate. Is only obtained in 0.02% of events. Do you see the difference there? In the general population, one person out of 10,000 has this disease. Okay. So you decide to go in, you don't have symptoms, but you're bored on a Tuesday and your computer died or there's no power in your room and the Wi-Fi doesn't work. So you decide you want to go get tested for a disease that you don't even know if you have. Okay. And so you go in a health center, you take the blood test and they say, you have the disease. You call your mom, start crying, make your last will and testament. You go to a crowded party. No. No, you went to the health center, you're definitely not a party goer. Okay, so you're positive. What is the probability? That you have the disease? Stop, what kind of rights? Oh, and I need a question. This is a classic problem using cases. Very common, it's very easy to understand. You have a population of people, 1 out of every 10,000 is sick. Okay? And you have a test. And the test can give 4 results, right? What are the 4 results it can give?
False positive, false negative, positive, and negative.
Good. That makes sense. So breaking that down a little bit more, it can give a positive test for someone who has it. It can give a negative test for someone who has it. It can give a negative test for someone who doesn't have it. And it can give a negative test for someone who does have it.
But we only care about 2 of those?
Well, you got one of the results.
Yeah.
So the question I have here is, you have a result. What is the likelihood that you have the disease? Just wondering, what are you talking about? So voodoo witchcraft?
So probability, so A would be that we have the disease, and then B is that we're,
We have to do it for each test.
I have given you enough information. You have this.
Okay.
And this alone will tell you, but the real art here in doing this type of a Bayes problem is knowing what goes where, right? So your question is not bad, I just don't want to give too much away.
Okay.
Right? So spend a few seconds thinking about which each of these things might mean for the pieces of information that I gave you. What does this say here, right? What do these two things mean? How would I read this in English?
likelihood that you are positive and got a positive test.
What do you mean positive? Because you are positive.
Oh, that you are diseased.
Right, so what's the likelihood that you're sick, given the positive diagnosis? What's the likelihood of sickness, given the positive diagnosis? Remember, that's why we use the word given and we have this fun bar. Because even though these things look intractable and weird letters, one after the other, they do mean something. So we can use English, we want to calculate this. And now that we know what these mean, we can understand what all of these mean. Right? Yes, sir. That's right, I'll be quiet.
That's one of the things about, right?
We want to put our money where our minds are? Does anyone want to bet on this one? So you saw how I did it last time, right?
The bet that we got the right answer, right?
No, you will have the right answer or you won't. You have your numbers in front of you. I will use one of these two numbers to calculate whether or not you are below or above the threshold. Generally speaking, I am doing what anyone will do when they computer simulate probabilities. So what they'll do is they'll say, let's say the probability is 0.5. Okay, then you will randomly generate a number between 0 and 1. If that number is below 0.5, the event doesn't happen. If the number is above 0.5, then the event does happen. So there is a probability that's obviously written down that I know what it is. You have now rolled numbers. One of these numbers I will choose. Look at the distribution of the numbers you have. If you know the probability ahead of time, you might look at your numbers and be like, oh, fuck, right? Because you know that neither of your numbers will work, but maybe one of them will work and you might want to bet. Does that process make sense?
So I can choose one of your numbers?
If you know what the probability is, you're not confident in the probability, then maybe none of you.
Wait, one more time, so like for Reed, if it's 60%, he would get it, 'cause it's.
So
Or
60% would be what out of a sided die? The 6 out of 10 is 3 out of 5.
Mhm.
Right? That's not really exactly on the die. Where is that on the die?
Yeah, I don't understand. It's-
Okay, 1 is 1 out of 6. Good. And what is 2 out of 6?
The third.
0.33. Okay, what is 3 out of 6? 0.5. Right? What is 4 out of 6?
2/3, 0.66.
0.66. So let's say the real probability is 60%. Then the 1, 2, and 3 are valued numbers that we will accept, right?
Yeah.
If the probability is 40%, then we lose and we only get 1 and 2. If the probability is 25%, then we lose and we only have 1 out of 6 chance. Depends on how big the probability is.
I'll bet $5.
Here's $5. Is that it?
Okay, so. Never mind, I'll let you think about this.
We don't know yet which number you're picking.
I know which one I'm doing.
Yeah, but we don't.
Yeah, you don't.
You don't know which number?
I know which number you're picking, there's a column of numbers and then a column of numbers, right?
Yeah.
Or I could read them as a percentage.
Column numbers. Okay,
I'm telling you, I've decided already.
okay.
All I'm saying is it's some selection of the numbers you provided, either the sum, the reading, right? The numbers that are here, you have in your mind the right answer, right? Because you did the calculation perfectly. So you know that you either need blank or blank or blank, right?
One of my numbers is good, one of my numbers is good.
That it? We done?
Yeah.
I'll bet $10. Reed's betting $10.
Yeah, I guess.
So if it's the percentage that you pick, it's just hypothetically, it's the percentage you pick. If it is or is below that, then we have the disease, and if it's above that, then we don't.
No, he's just doing the betting right now.
So we're trying to determine whether or not you are positive. What is the probability you have the disease? So you are currently betting, right, on whether or not you actually have the disease. And if your number is below the probability, then you have the disease. Otherwise, you don't have the disease, but you do lose your mind. Okay, we good?
Yeah, I think we're good.
What's the probability?
I think it's right.
4%?
Yeah.
It's a little too small.
Yeah.
A little too small.
I have 33.
33%? Okay, how'd you get there? Let's go through, let's walk through this process together. So I said A given B, so that's this, right? Probability of A given B. Okay, so what about this first one? What's the probability of A? What does that mean again?
Probability
That you
that,
have the disease.
That I have the disease, given the positive test result. So I could be like this, but I could go in here, I could be like, what's the probability of given positive test?
yeah,
Right? Okay, so let's go through and let's do that substitution everywhere. So, maybe I'll do it. Okay. So this was A. Yeah, right down. Shouldn't have deleted them. Let's do all A's. So the probability of sickness. Then what's this?
Please.
Oh, very good. Everyone's ready for that one. Okay, and then this one. That's like, he's like more like chill. Okay, and then this one.
Positive test.
I will strongly recommend doing something silly like this, at least when you're first learning. There is nothing that's more fucking complicating than complements of A and junction A, B, like you just can get lost so easily. So we all use emojis already, right? When I was growing up, we didn't have emojis. I know that's how fucking old I am, right? So it was like algebra was different, but like we already have a symbolic representation of what we're doing. But if you write this down, either in your notes or wherever else, you can use symbols to mean anything. And this is what we'll do. So what's the probability here of sickness?
1 out of 10,000.
So that's this one, right? Right? Okay, what is the probability of a positive test given the fact that you're sick?
Positive.
0.99.
Exactly. Good. What about this one? We already have that one. What about this one? We already have that one. That's the same. What about this one? What's that?
9,999.
So it would be,
1 minus.
1 minus.
good, yeah, 1 minus this rate. You get it. Does that make sense then? How that's calculated? Okay, so that's this rate, and then what's this rate?
0.02.
And what's the number you got?
132.
Thank you.
Is that correct? No, it is correct. 0.33 is that number, and that's the number. Good. Okay, so Rolando wins. And Reed wins. But so would have Jeff. That's 2 out of 6, right? How much money did you put down? You put down 5.
I would bet all my money.
I would have bet all my money. Okay, so another way we could do odds like that is that we could roll the die and those could be your 2 digits. And sometimes I'll read them this way and sometimes we'll read them that way, but usually you want to roll low no matter what.
Yeah.
Okay. Damn, that took me a lot longer than I thought. We're not shrugging, I'm way over prepared. I'm thinking that we'll get through like 3 pages of this notes and we get through like 1.5, like this. Okay, let me ask you a different question. There are 7 people in this room. You probably already know each other. Do you know whether or not anyone in this room has the same birthday?
No.
No.
You know everyone's birthday in this room?
We all celebrate each other. I don't know. if
I
we had
keep it in my
birthday party.
calendar, I would know if people have the same birthday.
Yeah,
Yeah.
Sarah's actually.
Really?
I don't know.
Yeah, the
his
only
birthday.
person's birthday I don't know is Reed's, but
Reed,
seeing.
what's your birthday?
Oh, that's actually true.
I know your birthday, I have.
You have it?
Yeah.
Yeah. we can-
You wanna know a fun party trick? This is a betting party trick, okay? So this one does leave this room, but you can't say where you got it.
Okay.
Okay, you're at a party. There needs to be at least some number of people. And we're gonna figure out exactly how many people there needs to be. You make a bet for some amount of money against some other dumb person in that room. You say, I bet 2 people in this room have the same birthday. Right?
Well, the trick
I
is just
just
know
know
if
the number and I.
The trick is know everyone. No, in a random, you could be at a random party, right? It's your first time hanging out with all these people, right? But it might be their first time hanging out with all these people too. You say, all right, we're gonna go around with a piece of paper, right? We're gonna write down everyone's birthday, we're gonna see if anyone matches. So you could think to yourself, what the fuck are you talking about? This is getting into an idea of what we call combinations. What are the different ways in which a selection can be made? So if you notice, for example, there's these different piles of money. Okay, so I can put them like a reasonable human being. I can take them and I can sort to them. Oops. Fuck. I can sort them like that, right? That's reasonable. Is that the only way I could put the money down?
No.
No, you could be unreasonable. Right? You could do that. You could even do this. Yeah, you could put, oh yeah, you could arrange them by color, right? And each one of those is a different choice. So if, for example, I only had 1 of each of the bills and they all fell out of my pocket, what is the probability that they land in a rainbow? You see? Some of these questions, like we're talking about die, or we're talking about rolling 2 die, you could count them. You're like, well, the 36, I just put up a little board and then I count them all up. But for maybe 7 combinations of number, yeah, for 7 different money types, now it's a little less obvious how many different combinations there are. So part of our idea of probability, definition of probability is what again?
The event you want.
Oh, summation of-
over everything.
The number of events A over the number in the sample space, S. Good. So sometimes we have to count. We have to count a lot of fucking things. Okay? You'll notice over here, how did we get these numbers?
Yeah, the count.
You had to obtain data, right? You had to measure from a bunch of sick people who had COVID, how many times the test worked. That is a number. 1 person out of 400 slipped through. Boom, that's the fraction, right? So we tend to disconnect in our mind the idea that these probabilities ahead of time come from an underlying population. And we'll get into the philosophy of that in a little while. But in order to do this part here, we need to be able to calculate the choices of A and the sample size as a whole. So we're gonna learn something called permutations and combinations. Okay, so let's ask the first question. How many ways are there to arrange this on the table?
Just that single.
Yeah.
one.
Good. All right, how many ways are there to arrange these on the table? So how's that? Show me that.
1 and 5 and 5 and 1.
1 and 5, and then 5 and 1. Those are the only 2 options, because this is identical with this, it's not a new option. How many ways are there arranged? 3. How do you do that?
I
Smart like that.
learned, I did permutations once.
Alright.
The second-
Trinity doesn't get to answer anymore. Why are there 6? What are the options?
1, 5, 10, 5, 10, 1, 10, 1, 5. And then there's other ways with.
You want to try? Do you know them all?
I don't know them all, I just know how many items you have for choice.
What was that word you said? Did you read the book?
No.
Oh my goodness, she's smart as, okay. So what does this mean factorial?
Whatever number you have multiplied by all the other
rest.
integers descending until.
Okay. The process make sense?
Yeah.
Have you ever used this in your whole life?
Yeah,
Like regularly, like in a day to day?
Yeah. Every
Yeah.
No, you don't lie to me. Okay, so what is n factorial? How do I write that?
N times n minus 1. You get to. N
My favorite symbol in the whole world. The
1,
N minus
n minus n would be,
0.
so you would never, that's never correct, right? No, it can't be. Then everything would be 0 for infinity. What is n factorial?
0.
That. What is 0 factorial?
1.
Gotcha. Okay, so for these 3, it's 3 times 2 times 1. 4. Or what is 7 factorial?
5,000.
What's that?
5,000.
Oh, wow. She knew where I was going. So there are 7,540 different combinations of the order in which I could place my money. Right? So what are the odds that it comes out in a rainbow? Yeah, so pretty unlikely, right? Good thing we didn't take that bet. Okay, is that reasonable?
Yeah.
Okay. Let's ask a different question. What if we only want the 2, like, or I guess these 3, like, these colors to be adjacent to one another? So let's say I only want, they all fall out of my pocket. And I don't really care about the rainbow too much, I just like when like similar colors are together. And like these really, to me, being colorblind-ish, right, like man, like I can't tell the difference, that's yellow or orange or whatever you want to call it. So as long as they're together, I'm happy. Now what?
Additional.
Conditional what? How would I do that?
You do the probability of how those can be laid out. With everything else.
So this is gonna be called a permutation. Okay? And we're gonna use this definition from our book. It's a little funny looking. Get rid of the word base, because that's not needed anymore. So the permutations would be the allowable choices given a set of possible things to choose from. So what I mean by that is, as long as k is less than n. So as long as these 3 are less than the 7 choices that I have to make, I can always write that there are I don't know why I don't give myself more word space. I was erase it, I regret it, okay. Okay. Given that there are k less than n choices, in this case, we're thinking 3 is less than 7, so that's valid. Okay, we will have n times n minus 1 times n minus 2, so on and so forth, all the way down to n minus k plus 1. And this is the definition of something that looks like this. N factorial over n minus k factorial. And we define this as n p. Okay. Dumb, right? Let's see if we can use it though. Okay. So what are our choices here? So we said that N was 7. And we said that K is
3.
how many choices?
And then it's 3 by 4.
Yes, is this a probability or is this the number of combinations that we can make?
Number of combinations.
Yeah, that's okay. It's fine. We're still learning with this. Right? So the nice thing about dividing factorials is I don't have to do a ton of math. I just have to do the difference. Well, so I still need to do it out because I'm not that smart. 7 times 6 times 5. And then 1. Right? Because all the fours and below cancel. So what did you say?
Then I just,
I don't know. You think I know?
7 times 30,
So that's 42 times 5.
or you can do 30 times 7.
Oh, it's 210.
It's 210. Good. Okay, so what did I write? So 210 what?
2 times number, yeah, 2
Get what you
times
want.
combinations where like those 3 colors are first.
Are together.
Yeah.
Good. Not necessarily first, just together.
That's good.
Good. So let's ask a different question. So what's the probability that my 3 colors are together?
205,000.
Good. So it's something like 210, the ones that I want, over
Sure, I know.
2040.
50, 40.
Oh, 5,000. Okay. Good. Would you take those odds?
No.
2 out of 50? Not pretty good. Well, sorry. I took you over. If you have questions on the homework or whatever, fill out the when to meet so that we can do office hours, and I'll set office hours. I'll probably try to do 4 30-minute sessions a week. You say that you're only available on Friday, please be honest, because I don't want to come in on Friday if no one ever comes to office hours.
How are you looking at me? I know we are.
I'm only looking in the direction of the whole class.
Ah,
Are we walking together?
Wait,